This tutorial shows you how to conduct the mixed ANOVA in R and interpret its results. Its purpose is testing different groups over time for differences for a test variable. For example, I want to test a new drug for efficacy. I will divide my sample into two groups, an intervention or experimental group and a control group. This controls for the between subject effect. Furthermore, I want to see the results over time. I'll establish a baseline measurement and 3 follow-up measurements for both groups. This will take care of the within subject effect. The requirements for the mixed ANOVA are the following. A between subject effect, meaning at least 2 groups of individuals, usually a control and intervention, aka experimental group. A within subject effect, meaning repeated measurements for all individuals. A dependent variable on the interval or ratio scale. A normally distributed dependent variable for each combination of the within and between subject effect. Homogeneity of variance for the between subject factor at each level of the within subject factor. Homogeneity of covariances of the between subject factor, and equal variances of the differences for the measurements, also called sphericity, but only if you have 3 or more measurements over time. Sphericity testing is based on the model calculation and will be shown during this video. Assumptions 5 to 7 are shown in separate videos to keep this one as concise as possible. Before starting, please make sure your data is in the so-called long format for the analysis to work. As a first step, I want to see some descriptive statistics to get a first idea of my data. One can use the convenient dplyr package and pipes. Start with the group by function and put in your time and group variable. For convenience, here simply time and group. Follow this up with the pipes operator and use the get_summary_stats function on your test variable, here simply value, and within quotation marks give mean_sd as the type for desired stats. This will produce mean and standard deviation. With less complex models, one can usually see if trends might be present. In my case, the mean is slowly increasing for the experimental group, with a rather constant mean for the control group. You can also visualize the means for the 2 groups over time using box plots with the ggboxplot function. Simply put in your data frame, followed by the test variable as y, the time variable as x, and the group variable as the fill argument. You can also swap the x and fill argument, whatever suits you best. The interquartile range is represented by the height of the box and the median by the black horizontal lines, respectively. If you have circles above or below the whiskers, those are values that have the 1.5 times interquartile range distance to the edges of the box and are sometimes referred to as outliers. If those are plausible values, you have no reason to worry and can continue. Now I finally want to test whether the group means, the means over time, or a combination of both are significantly different from each other or not. I use the ANOVA_test function of the R statics package. Within the ANOVA_test function, I start off with the data frame. The argument dv represents the dependent or test variable. The WID argument is the ID variable that is required to properly match the measurements to individuals in long format data. The between argument is for the between subject factor, the group. Finally, the within argument is for the, you guessed it, within subject factor, the time variable, simply telling R at which point in time the measurements were taken. I can run this one line and get my results. Since I have to look at sphericity first and maybe apply a correction, I will start with the Marshalls test for sphericity. The null hypothesis for this test assumes equal variances for the differences over time, aka the within subject effect. If your p-value is above the predefined threshold, you can observe sphericity in your data. In my example, I have to reject the null hypothesis of sphericity. In such a case, the ANOVA will automatically apply a Greenhouse-Geiser correction for non-sphericity by default. If you desire a different correction, however, you can use the argument correction equals within the ANOVA_test function. However, the 2 most common corrections are shown in the results anyway with Greenhouse-Geiser and Huhn-Feld. The interpretation of the ANOVA results is straightforward. Reminder, the null hypothesis assumes no difference of the means for the given within subject effect, between subject effect, or their combination, aka interaction. Eventually, you always have 3 possible effects. The trained eye will look at the interaction first, and then decide whether to look at the within or between subject effect. I will go through each effect to cover all possible cases of significant effects. Let's start with group differences, aka the between subject effect. I can see that my p-value is 2.14 times 10 to the negative 5. This implies, without considering the time or within subject effect, that I can observe differences across the groups. My descriptive analysis already revealed that the experimental group had higher means, almost throughout, except for the baseline measurement in t0. Next, I'll look at the time differences, aka the within subject effect. Caution, since my sphericity test rejected the null hypothesis, I have to look at the sphericity correction results below. Correction is applied to the degrees of freedom. One can see that the correction with greenhouse geyser is larger, making it a more conservative correction. This is usually the safer approach for samples that exceed small sizes. My p-value after correction is small enough, with 0.01 for greenhouse geyser and 0.009 for Hune-Feld. I can therefore conclude that the means over time are different. My descriptive analysis showed, however, that the control group had an almost constant mean. Therefore, the within effect is mainly driven by the experimental group, which poses the question of a possible interaction of the within and between subject effects. Or put another way, is there an increase or decrease of the mean over time for only one group, ideally the experimental group? To answer the question, you have to look at the interaction, in my case, group: time. Keep in mind that sphericity, or its lag, is also relevant for the interaction. In my example, I therefore have to look at the corrected interaction results. I can see a p-value of 0.01 for the interaction. I can therefore conclude that an interaction between group and time exists. If this is the case, within subject and between subject effects themselves, sometimes referred to as main effects, should not be interpreted anymore. We just found out that they depend on each other and should therefore not interpret them while holding the other effect constant. To fully answer the question between which measurements over time difference exist, you have to look at post hoc tests in addition to the interaction, which is shown in the following video.